Naive RAG can be divided into three processes: indexing, retrieval, and generation. What is indexing? Indexing external documents. The external database will be split into smaller pages embedded into vectors, vectorized, and then stored in a vector database. Second is retrieval, which means the user's query or search will be converted into an embedding, and from there, used to find the most relevant document pages in the vector database. Third is generation. That is, the user's queries and the pages that were retrieved in the second step will be sent to an LLM model. Based on information, it will generate accurate and relevant answer based on the information from that database. So as you can see, there are still a lot of limitations with this approach to RAG at the basic or naive level. That's why it leads to a need for a more powerful RAG framework, one that's more advanced, that can address issues of basic RAG. A story about continuous improvement, moving from simple model, simple process, system sophisticated, complex, and more optimized at every step. From there, it will require methods of advanced RAG or enhanced RAG, which necessitate a change in the model, focusing on optimizing the entire process. At this stage, it will require a series of improvements in a modular fashion, that is, modularization aimed at specific weaknesses of the method. Naive. Here, we can divide it into three modules that can be improved: pre-retrieval, retrieval, and post-retrieval. Before retrieval, retrieval, and after retrieval. Hello, hi everyone, I'm Min. Duck, welcome everyone to this video, new one of mine. So in this video, let's explore together Retrieval-Augmented Generation, or RAG for short. AI is still developing every day, and its applications are also very diverse. But for businesses, the simplest, most common, and most practical application is RAG. So what is RAG and how you apply RAG to your business? Let's find in video. Before we get into explaining the definition of RAG, we need to understand the problem that RAG solves and why we need to use RAG. First, we need to understand the core limitations of large language systems, LLMs, large language models. First, in terms of information access, here I've listed 5 basic issues that are inherent to LLMs. The first is outdated, non-updated information. LLMs are trained on datasets of large data, but this data has a cutoff point. Therefore, their knowledge can become outdated, leading to responses that do not reflect the current events or the latest information. The second issue is hallucinations, which means hallucinations. LLMs tend to hallucinate, producing responses that sound reasonable but are inaccurate or make no sense. Third is the lack of knowledge. LLMs have knowledge that is very broad across all fields. Industry fields specialized in any one specific field. For example, if you want to adapt a general-purpose LLM to a specific field, like law, medicine, or simply the internal knowledge of an organization, then you'll need to take an extra step called fine-tuning. As for the LLM itself, versatile, in-depth expertise. Fourth, it lacks transparency and traceability, meaning the trail. What does that mean? It means LLMs provide answers without references, making verifying the accuracy or those claims or those statements, its conclusions, very difficult, even impossible. Fifth, and lastly, it's very expensive to train an AI model. If you want to train or fine-tune an AI model, large language models, to integrate new information or adapt to new fields, it will be very costly in terms of compute power, that is, computational power and time, as well as financial investment. So those are the core, inherent issues of large language models. From there, it creates a need to find a solution to address or minimize the inherent limitations of large language models. And RAG, Retrieval-Augmented Generation, is exactly such a solution to improve LLMs. It will address the issues we've mentioned. First, it will help update new information. RAG will connect LLMs to external knowledge sources. so that it can update in real time or more frequently compared to the internal knowledge already present in the LLM from the training data. Second, it will reduce hallucinations by basing its responses on the LLM's output and the actual retrieved documents specifically to provide its conclusions for its own conclusions. As a result, it will reduce the likelihood of generating unverified or even fabricated information. Third, it offers a way to add specialized knowledge. So RAG is an effective solution by allowing the LLM to access and use information from external databases that we provide, so it fits the fields that we need. Fourth, it improves transparency and provenance, meaning that the RAG system will provide reference materials that are retrieved and used to generate answers. As a result, it will also provide, be accountable for information that is. And finally, it improves cost-effective. RAG provide more cost-effective approach to bring new data knowledge the LLM system versus other methods such as fine-tune a new model. From there we will come to a simple definition of RAG. You can understand RAG as powerful AI framework helps improve and upgrade large language models, LLMs, by connecting them to external sources of authoritative knowledge, because just relying on internal training data, initially static information data, then the LLM will be able to retrieve relevant information and up-to-date content before it generates a response to the user's question. This process will make the output of the AI more accurate, more reliable, and better at understanding context. So you can understand the 3 words in retrieval-augmented generation like this. Retrieval means retrieve to access or pull relevant data from the knowledge base. Augmented, enhanced, amplified, combining user's query with relevant data retrieved from database, knowledge base. And generate here means to provide an answer, to create a response based on the context provided based on the relevant data it pulled from the knowledge base. Alright, in this slide I also point out some practical applications of RAG in work and daily life. So the capability of RAG in generating content. RAG will address the core issues of LLMs, and from there it will provide very practical applications in many fields, especially in areas that require in-depth knowledge and expertise. For example, building a question answering system, which is a system that answers questions. This can be considered the prominent application of RAG because it helps improve the accuracy and detail for domain-specific questions, meaning those that require deep expertise. Secondly, building chatbots to support customers and other conversational. RAG creates smarter AI chatbots for customer support by accessing databases, user manuals, FAQs, allow for better personalization by retrieving specific user data. Third, is search and knowledge management for businesses. It will function as a natural language interface that uses internal knowledge bases of the business, improving productivity. Business decisions. It allows employees to find answers to relevant questions about company policies or projects or any other information in the database. Fourth is a small application for those who work with content, read, and create. Support in retrieving data and compiling statistics from the database, or have to do things like summarizing long documents, or automating tasks, or querying information. And especially with RAG, it will help us build applications tailored to industries that are highly specialized, such as healthcare, finance, law, education, or e-commerce, or software development. Alright, so in this slide, I'm going to explain the core process at the heart of basic RAG, or naive RAG. A naive RAG can be divided into 3 processes, or 3 main steps: indexing, retrieval, and generation. So what is indexing? Indexing means external database will be split into smaller pages, embedded into vectors, and then stored in a vector database. Second is retrieval, which means the user's query, their retrieval, will be converted into an embedding, and from there, used to find the most relevant document pages in the vector database. Third is generation, which means the user's queries, and then the pages that are retrieved in the second step will be sent to an LLM model so that it can Use all that information to generate the most accurate and practical answer based on the information from the database. This is a diagram that I think explains very accurately, and the three main processes of a naive RAG or basic RAG app. So now I will break down this diagram to explain each step one by one, so it's easier to understand. One is indexing. This is a preparatory process, a step before retrieval, kind of a pre-preparation step. When external knowledge sources of information, have been prepared in advance to help make querying more effective, there will be sub-steps here like data ingestion and preparation, external data from many sources like websites, document repositories, databases, or PDF documents need gathered in one place. Second is chunking. Documents will be split into smaller sections, easier to manage, called pages. The reason for chunking is that smaller text segments are more likely to contain specific information and are easier for the LLM to process within a context window. A context window. To chunk, it could be splitting by a fixed number of characters, or by sentences, or by paragraphs. For specialized source code, there might be analyzers, AST segmentation. Next is embedding generation. Will then be converted into an embedding, which is a vector number, by using a language embedding model called embedding language model, for example, OpenAI text embedding or Mistral AI. These embeddings will capture semantic meaning of text pages, so that the pages that have similar meanings will have embeddings close to each other in a vector space. I'll add a part to explain this simply. Next is vector storage. Vector storage system. These embeddings created with text pages be stored in a specialized database called a vector database or vector store. These databases are optimized to search for most efficient sim of vectors, multiple dimensions, high-dimensional vectors. Second is retrieval. So this process happens at the time of inference, which is the inference moment. When the user sends a query to the LLM, there will be two main parts. The first is query embedding, where the user's input query is converted into an embedding using the same embedding model that was used in the indexing step. The second is similarity search, which means related search, searching for the similarity, which will be done by comparing the query embedding with all the chunk embeddings that are stored in the vector database. Finally, it returns pages with relevant information to query. Here's diagram to illustrate this vector search process. So you can imagine that the information will be vectorized. It will be transformed into vectors as points in a certain space, and the pieces of information that are related to each other, that are close to each other, be where near. For example, in this illustration, animals will be in a region of space related to each other. Those related to cats and different types of cats will be very close together. And similarly, things like fruits, fruit types, they will also be in a region that's very close together, which is called vectorization. For example, here is an apple, right? Apple. It could refer to a type of fruit, but it could also be the name of a company. That is, Apple the company. And if Apple is a company, then it will be close to Google, which is another company. So this kind of vector search will return items that are thematically related, meaning semantics, instead of searching by exact keywords. Vector search, or also known as vector similarity search, is the process of querying a vector database to find vectors and related data that are similar to a given query vector. Similarity is determined by the closeness of vectors. The third process of a basic RAG application is generation. This is the stage, the final section, where LLM answers the person's question. It has two main parts. Prompt augmentation are the text pages that will be retrieved in the step above and combined with the user's original queries to generate an augmented prompt. And prompt engineering techniques will be used here to structure an effective prompt, guiding the LLM on how to use the provided context. Then, LLM response generation. These augmented prompts will be sent to a large language model like OpenAI's GPT or Gemini or Claude. And these LLMs will process the input and generate the best response based on the retrieved context and the answer to the user's query. So that's basically the three core processes of a basic RAG. First is indexing. The documents will be split up into smaller pages, then embedded as vectors, and stored in the vector database. Second is retrieval. That means the user's query will be embedded to find relevant pages database. Third generation, users query relevant pages are retrieved and sent to an LLM model to generate the final answer from database. Although basic RAG provides a simple approach to integrating a knowledge base, this simplicity also comes with certain limitations and challenges. Here, I'll also list out a few limitations of basic RAG, such as retrieval quality, which isn't high, with low accuracy and low coverage. Then there's the issue of data filtering and redundant data, because retrieving multiple pages, it can contain duplicate information, redundant, which leads to the responses generated by the LLM also being repetitive and wordy, even rambling. Another quite serious issue is hallucination, which still isn't completely resolved because if the context being retrieved contains a lot of noise, or is irrelevant, or even contains conflicting information fighting each other, then the LLM can still experience hallucinations, or it might ignore the provided information, the additional context, and revert to using its parametric knowledge, which is the built-in parametric knowledge in its training data, won't be able to avoid giving information not segmented anymore. The next issue is the limitations of the context window. LLMs have a certain context window size with limited context, even though the context window has already been upgraded and gradually increased over the past few years. For example, with Google's thinking AI models, the context window has reached up to 1 million tokens, even 2 million tokens. But connecting many pages being retrieved or pages too long, they can exceed the limit of this context window. But even in cases where it's still within the context window, because the context window is too long, it can still run into the problem of lost in the middle, meaning that the information in a prompt is too long to be used effectively. Next, the issue of the limitation context can have difficulty fully and accurately understanding information to provide final response. Unclear or ambiguous output, or even irrelevant to the user's query, even though there are related keywords in the context. So this relates to understanding the question and getting the context right. You see, humans can read between the lines, meaning we can read a sentence but understand the underlying meaning behind it, but LLMs often, it can't really do that, meaning it can have semantic drift when the responses drifts from the original intended meaning implied by the context. Finally, there's a big issue, is a major issue with RAG. Basically, it's very difficult for it to answer complex queries, complex questions that require reasoning, thinking, connecting multiple pieces of scattered information, understanding of a particular expertise of a specific field, even though retrieval can retrieve relevant document pages, but the generation model might not be able to synthesize the response accurately because it will just return that information, but there's no step where it can reason by itself, or infer, or make its own arguments, again to come up with the final answer. Right? So as you can see, there are still quite a lot of limitations with that basic level RAG approach. Naive, that's why there's a need for a stronger, more advanced RAG framework that can address the problems of basic RAG. So here, it's really a story of continuous improvement, moving from a model, a simple process, to a system that's more sophisticated, more complex, and more optimized at every step. The evolution here from naive RAG is a method that was initially very simple to set up the core 3-step process of index, retrieve, and generate. As I just explained, it faces retrieval limitations with the context window, and especially the risk of hallucination. Context noisy, contains a lot of irrelevant information. From there, it requires advanced RAG solutions, which are enhanced RAG approaches, requiring a change in the model, focusing and optimizing the entire process. So at this stage, a series of improvements in a modular fashion will be needed. Modularization targeting weaknesses. The naive approach. We break it into 3 modules to be improved: pre-retrieval, retrieval, and post-retrieval. Before retrieval, during, and after retrieval. So before retrieval, we need to improve the quality of the data and build the query before we start searching in. Database retrieval uses sophisticated search and ranking. Retrieval done, continue to fine-tune and optimize the context. Retrieve before generating final response content. Here, I also have another line about the self-correcting architecture, which is self-correcting architecture. A self-correcting architecture where the AI evaluates and corrects its errors. A system like self-RAG, corrective RAG, frameworks will introduce an internal mechanism so that the AI can self-evaluate, self-criticize, self-check, and self-correct, which makes RAG more autonomous, powerful, accurate, reliable. Next, I have a slide to compare RAG with alternative to RAG is fine-tuning. This topic is also a big one, and it's quite complex, so here, I'll touch on it briefly and keep it simple. The difference between RAG and fine-tuning is that RAG is an AI framework designed to help improve generative models, the LLMs, by integrating retrieval into the LLM to generate the answer. It will automatically retrieve and gather the relevant information from external sources to provide to the LLM at inference time. On the other hand, fine-tuning involves training a large language model, LLM, that has already been pre-trained, but this time, we'll train it on a smaller, more specialized dataset to adjust the internal parameters of that LLM to optimize it for a specific task or domain field. A table comparing RAG and fine-tuning across several aspects, such as the accuracy returned results, interpretability, trust, and latency and scalability of the knowledge base, and the feasibility, the ease or difficulty of implementation of the RAG method into production for your reference. Okay, so in this video, I introduced you to RAG, or Retrieval-Augmented Generation, the problems that RAG solves, why we need RAG, and the applications of RAG in business and enterprise environments. Then, I also went deeper into explaining the mechanism of RAG, naive RAG, with three main processes, which are indexing, retrieval, and generation. Although RAG is very powerful, and basic RAG is also quite interesting and has many features, but it also has certain limitations. Exactly, because it's not perfect, it still hasn't completely solved the problem thoroughly. From there, it leads to the need to develop basic RAG into advanced RAG, more advanced techniques to achieve results, solve problems thoroughly. The results returned by the AI will be more correct, more accurate, and more reliable. Hopefully, you've learned something from this video of mine. If you found this video helpful, like and leave a comment. I'll give you a detailed guide on how to build a basic RAG chatbot application in N8N, which is my favorite AI automation tool, if you're still here watching. See you!